Hello, 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 hello. So we are back with our study series, and this time we're gonna tackle the Docker course. It's just something which I do require to know, and yeah, let's get on with it, I guess. Yeah, some intro. So there are multiple technologies I have to know, and the last time I was streaming, I guess it was June and April, with Python. And these series or these when I stream, and it's really mostly it's unknown information for me. Like every time I do this, and it does look like I remember when I was doing the Python for everybody, that I was like quite demotivated by the end, and I was very confused. But then, at my own pace, after I did all of the streaming, I did it again on Coursera, and now I'm actually using Python, and I have a understanding. Let's say I can read the code, and so even what why I'm saying is this is because if I look, demotivated or frustrated during the, I just say it in advance. It's my focused face and everything, and even though it may seem like that, it's definitely the learning is happening regardless. And then when you don't even realize that, wow, actually I know stuff. So yeah, being confused is part of the process, and it's fine. Let's do it. Let's just do it. I have not much plans really for the day. It's 12:30, so let's get on with it. We can maybe follow in this day one, day two, day three. So I guess we can do it like this. We will do under 44 minutes mark today. So set achievable goals. Um, yeah, I have two screens. Scenes. So I'm gonna switch back between my notes because one was very important with my Python for everybody course, that I was really taking everything like super detailed notes, and you as you make your bullet points, make everything stick, you create this internal map, I would say. So yeah, I will probably pause the video multiple times. Yeah, and I have to mute myself because it's on speaker and it's gonna bleed into it. So yeah, we're gonna see how it goes. So let's do it. Let's do it.
Hey team, welcome to this complete course on Docker and containers. My goal with this course is for it to be the most efficient way for you to ramp up on your Docker and container skills, starting from the basics and progressing through to intermediate and advanced concepts. By the end of the course, you'll have the knowledge and skills to be productive within a team using containers for both development and deployment of their applications. You'll understand why you would want to use containers, as well as how to integrate them seamlessly into your own workflow. This course is split between theory and practice. For each section, I'll cover the concepts that you need to know using helpful visuals and diagrams before diving into our code editor and solidifying that knowledge with real-world examples. I've provided a companion GitHub repo linked in the description containing all of the code and configuration that will be shown throughout the course. Feel free to clone or fork the repo to follow along as we go. Before diving in, I do want to highlight a couple of prerequisites that will help you get the most out of this course. As the image shows, it can be tempting to jump straight into learning about containers and skipping some of the foundational concepts that they build upon. I'll do my best to explain everything in such a way that even an absolute beginner would understand, but if you have some familiarity with web application development and how all the different components fit together, that will be helpful and make it easier to understand what aspects are container specific and what aspects are just general application architecture concerns. Also, having some understanding of basics Linux shell commands will be useful, as we'll use such commands throughout the course. If you don't have these, I think you can still get value from the course, but some things that I do or say might not make sense, so it could be worthwhile to go and brush up on those topics first. I've broken down the course into the following learning modules, each building progressively upon the last. I provided timestamps in the description to make it easy to jump between sections if you're already familiar with the topic, or if you plan to revisit this video and watch it across multiple sessions. In the first portion of the course, sections 1 through 4, we'll explore why containers exist in the first place, the problems that they solve, and the underlying Linux kernel features that make Docker and containers possible. We'll also install and configure the Docker desktop application and get our first hands-on experience running some containers. For the remainder of the course, we'll be focused on building out and containerizing our own web application, from development all the way through to deploying it to the cloud. This is where the rubber meets the road, and you'll learn exactly how software companies use Docker throughout the application development lifecycle. So what is this demo application we're working with? I'll go into it in much more detail during section 5 and throughout the rest of the course, but in summary, it's a minimal 3-tier web application, meaning it has a front end, in this case, built out using React, an API layer. We actually have 2 implementations of this, one in Node.js and one in Golang, to highlight how different languages are handled with containers. And finally, a Postgres database. Each service is designed to be as simple as possible while still showcasing how they all fit together within a real-world application. When we get to the deployment section of the course, we'll learn how to deploy our containerized application to the cloud. Within the course, I'll be using Docker Swarm, which is a container orchestrator built into Docker. And then I've also filmed 2 bonus videos to highlight additional methods of deploying containers, one using Railway and another using Kubernetes. These are separate from the course, and information about where you can find them can be found in the description. This should give you a taste of the variety of options that we have for deploying containerized applications. Before we jump into the course content, I want to pause for a moment to thank the sponsor of this video, Shipyard. Because of their generous support, I can provide this course to you completely free of charge. I'm excited about them as a sponsor because Shipyard is highly relevant to everyone working in the container world. Their platform offers the easiest way to generate on-demand ephemeral environments. In other words, automatically generating fully functional, isolated environments for every pull request. You connect your GitHub repo, add a couple of lines of code to your configuration files, and you can have test environments running in just a few minutes. Later in the course, I'll demonstrate how to use the Shipyard platform with the course sample application. As a bonus for all the students of this course, the team at Shipyard has created an exclusive coupon code for you. The first 300 people to create a Shipyard account and use the promo code DevOps Directive will get 30 extra free days on either the startup or business tier plans. Links and instructions are in the description below. You should go check out the Shipyard platform and consider how it can help your teams deliver better software faster. Without further ado, let's get into the course. Now, in this first section of the course, I really want to ground our understanding of why containers exist and why a product like Docker has been
All right, yeah, I'm making a pause here because Steam was jumping in, so limiting distractions, and I closed the application. I also must add that when I was used to streaming, I used the desktop PC with RTX 3090 and good processor and everything was much more smoother. Like really, it was working very nicely. And here I'm streaming, and already the Windows, even before the stream, I'm using my T480S laptop, which is, God bless this laptop, it's fine. I mean, it served me well, but yeah, it's currently my GPU is at the repair. So if hopefully it will be repaired, I will be very happy and to use it for the stream. But I feel like, okay, so it requires JavaScript, some knowledge, which I have absolutely zero. And bash commands, yeah, I mean, we use bash commands when we ask the copilot, right? Unfortunately. I mean, but yeah, you have some idea. Anyway, he says we can still continue. So let's try. I mean, we already started it, but and we gonna have to learn JavaScript anyway. Like this is just no question about that. So whatever happens here, it can be applied. The next step would be to do a JavaScript stream at some point. But let's go back because I wanna see I wanna already organize. So he said about the demo application.
So success.
And I think that's the point where I can basically just whoop. Because as you can see, it has all of the stuff, the layout of the course. Wow, okay. Everything is here. Yeah, fine. I mean, okay. So I cloned it. We can continue the video.
And I've also filmed as a bonus for all the first. I really want to ground our understanding of why containers exist and why a product like Docker has been so successful. We're going to start with kind of the motivation, and then we'll walk through the history of different virtualization technologies from bare metal to virtual machines to containers, and try to understand how that evolution has occurred and why containers have become the dominant kind of development and deployment mechanism for software applications today. And this meme on the right is one that I've seen shared a number of times. It's this idea that I'm building a software application, I get it running locally, but then something goes wrong in the process of translating that local system to the production one. And so one thing that Docker does really well is help to make it such that our local environment is as close as possible to the production environment that we're going to deploy to. And so that's what this is hinting at, is we're taking that local environment and just shipping it directly to production. Now, there's two main aspects of the software development lifecycle that Docker and containers are trying to address. The first one is on the development side. So upfront, as we're building this application, maybe historically, there was this long process. You join a company and they tell you, here's your new laptop. Go ahead and install all these things, run these scripts, and get everything configured. And now you can run the application locally and do your development. It was very complex, lots of opportunity for human error. And so then Docker came along, and now setting up your development environment is as easy as running a single command, Docker compose up. We're going to go more into what that is doing later in the course, but it took this whole complex sequence of events that you needed to run and turn that into a singular system and command that everyone can run and be up and running in the first hour of their day. And so making all of the different combinations of Windows and Mac and Linux development environments all compatible is one thing that Docker does really well, and containers in general do really well. And so that's kind of the development side of things. On the deployment side of things, similarly, let's say you would build your application and then you need to put it onto some server somewhere to run it. And there was this idea that there's a number of steps that need to happen. Let's say, okay, we need to create a server running Ubuntu. Then we're going to run some configuration software like Ansible to get all the dependencies configured. And then finally, we're going to copy our application code onto the server and run it with these configuration options. Again, lots of steps, lots of complexity, and much harder to ensure that it's going to be right every single time. What containers do is they bring a single standardized package such that as long as my server has a container runtime, and there's a number of those available, Docker provides one, but there's a number out there, all you need to do is take this standard container image and run it with these specific options, and that's it. So now instead of worrying about the underlying operating system and the underlying dependencies, as long as we have our system and a container runtime and our container image, we can run it and get repeatably reliable results over and over. And so these two aspects are really why containers exist. And you can see how much simpler it gets when we use containers, going from this historical system with lots of steps and potential for error down to a much more simplified, unified approach using a system like container and like Docker. And so that hints at what a container is. I've talked about kind of the standardized package, but from the Docker website, I've talked about kind of a system like container and like Docker.
Is there like a hotkey for muting this, by the way? Whatever. Yeah, I have to make note about everything. I cannot skip. I know what I was even thinking about, like, I'm gonna just go on, but no, I have to make sure everything sticks. Critically thinking about. That's why it's gonna take a long time, but fine. I should be learning from a book, to be honest. I should be learning from a book, like a good book, and read it out loud. That was working because I'm engaged. Whenever I watch a video, I get completely somewhere else. I don't know what's going on. I just like But if I read it out loud to get the development environment set up, install Postgres, MongoDB, and run these 5 scripts. Oh, blah 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 blah. Run Docker Compose up. So from this point, I get that instead of doing all the manual work, you can just run Docker Compose up. What does that even mean? Deployment. To deploy the application, provision a server running Ubuntu, run this Ansible playbook to install the dependencies, blah 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 blah, and configure the system, then copy the deployment binary and run it with these options. Run this container image with these options. So basically, instead of running these mundane tasks, run this container image with these options. It's not working. Literally Control V is not working. I'm making now a screenshot so that I don't have to type all of this out. And it's working. Okay. Yeah, and let's watch it back if we really understood this part.
Unify exists, and you can over and over under specific options. What you need to do is take you need to create a environments all compatible to a singular system. So then Docker came along and they tell you there was a life cycle that Docker and containers are trying. One thing that Docker does really well is help to make it such that our local environment is as close as possible to the production environment that we're going to deploy to. And so that's what this is hinting at, is we're taking that local environment and just shipping it directly to production. Now, there's two main aspects of the software development lifecycle that Docker and containers are trying to address. The first one is on the development side. So up front, as we're building this application, maybe historically, there was this long process. You join a company and they tell you, here's your new laptop. Go ahead and install all these things, run these scripts, and get everything configured. And now you can run the application locally and do your development. It was very complex, lots of opportunity for human error. And so then Docker came along, and now setting up your development environment is as easy as running a single command, Docker compose up. We're going to go more into what that is doing later in the course, but it took this whole complex sequence of events that you needed to run and turn that into a singular system and command that everyone can run and be up and running in the first hour of their day. And so making all of the different combinations of Windows and Mac and Linux development environments all compatible is one thing that Docker does really well, and containers in general do really well. And so that's kind of the development side of things. On the deployment side of things, similarly, let's say you would build your application and then you need to put it onto some server somewhere to run it. And there was this idea that there's a number of steps that need to happen. Let's say, okay, we need to create a server running Ubuntu. Then we're going to run some configuration software like Ansible to get all the dependencies configured. And then finally, we're going to copy our application code onto the server and run it with these configuration options. Again, lots of steps, lots of complexity, and much harder to ensure that it's going to be right every single time. What containers do is they bring a single standardized package such that as long as my server has a container runtime, and there's a number of those available, Docker provides one, but there's a number out there. All you need to do is take this standard container image and run it with these specific options, and that's it. So now instead of worrying about the underlying operating system and the underlying dependencies, As long as we have our system and a container runtime and our container image, we can run it and get repeatably reliable results over and over. And so these two aspects are really why containers exist. And you can see how much simpler it gets when we use containers, going from this historical system with lots of steps and potential for error down to a much more simplified, unified approach using a system like container and like Docker.
Yeah, so this makes sense because I was involved in a project and I would have to go through this setup, without using any container or Docker, and it was a pain. Like I know that I don't even know if this is applicable here, but I know that I installed not only the pip install type of packages, but also something like the make, like to be able to do make commands and just I just research what I can do and to install it and make it work. But it's a mess, right? And now or for example, I had to use a Streamlit app, and then the Snowpark library requires something like an earlier version of Python, and so I cannot use it in my environment. So it's just, yeah, it's a mess. So in my brain, definitely like this, and I know that in my production computer as well, I couldn't tell you what's going on. And my idea is that, oh my god, running again a new environment is like super painful. It's very confusing and it's just a lot of hassle before you even get there to actually make code or make actually like thinking tasks. So yeah, so very nice idea to read every page what he says, write it down, and then watch the video what he says. This is exactly what we're gonna do.
And so that hints at what a container is. I've talked about kind of the standardized package, but from the Docker website, a Docker container image is a lightweight, standalone, executable package of software that includes everything needed to run an application. So you can think of it as this box that contains the underlying sort of OS dependencies, let's say runtime dependencies. So if I was writing an app in Python, it would have the Python runtime with the version that is needed. It would have any of the Python libraries that I'm using. So maybe I'm using SQL Alchemy to talk to a database or Fast API to build out an API. And then it's also going to have my application code. So the specific application code that I'm writing, all of that gets bundled into this container image. And then the beauty is that we have this standard interface and can run multiple copies of it. So let's say I need 2 copies of this application. I can take that image with a container runtime and run a container, run 2 copies, run 3 copies, etc. And so I've used the term container and container image. It's important to know the difference there. A container image is this artifact that has all of these dependencies within it. A container is what you run from that image. So you take an image, and if you think of object-oriented programming, a container image is like the class, and then the container itself that you're actually running is like an instance of that class, an instantiation of that class. With a container runtime and run a container, run 2 copies, run 3 copies, etc. And so I've used the term container and container image. It's important to know the difference there. A container image is this artifact that has all of these dependencies within it. Image is this artifact that has all of these dependencies within it. A container is what you run from that image. So you take an image, and if you think of object-oriented programming, a container image is like the class, and then the container itself that you're actually running is like an instance of that class, an instantiation of that class. Itself that you're actually running is like an instance. Image is like the class. Take an image, and if you think of object-oriented programming, a container image is like the class, and then the container itself that you're actually running is like an instance of that class, an instantiation of that class. And so a container allows us to have this standardized packaging that we can then create one or more copies of, and those copies are going to be the same every single time. So far, I've been using the term Docker container, but I want at this point to call out what is known as the OCI, or the Open Container Initiative. And effectively, there were a few early players, including Docker, building out the early implementations of containers. And as they became more popular, companies realized that rather than having a whole bunch of slightly different but similar things that we're calling containers, it would make much more sense to come together and create one standard that can be used across different implementations. That's exactly what the Open Container Initiative is. A number of companies, including Docker, Google, VMware, Microsoft, Dell, IBM, Oracle, the list goes on, came together and created open industry standards around what a container is and how it should be run. And so there's three primary specifications that the OCI defines: the runtime specification, the image specification, and the distribution specification. So the image specification defines what should be included in the image in terms of metadata and the format that it should contain, so a serializable file system. The runtime specification defines how you would take an image that adheres to that image specification and run it in a container. And then the distribution specification talks about how those images should be distributed. So think about registries and pushing and pulling images. And so these three things together make up the Open Container Initiative. And Docker has a specific implementation of this standard. So when I talk about Docker images or Docker container images, what I'm referring to specifically is the Docker implementation of this OCI specification. It specifically is the Docker implementation of this OCI specification. If Docker is the only container tool that you're using, it's not all that important to know this. I wanted to provide this context in case you start using other tools and know that there is this standard format that can be shared across different tooling in the ecosystem. Now let's walk back in time a little while and understand how we got to this idea of containers. Hopefully from my description of the motivation, you understand why containers are useful, but I think it's also important to understand the history and the context of how we got to where we are today. And so before there were containers, before there were even virtual machines, we just had computers. We now call this bare metal computing. So if you're running your applications directly on the hardware system itself, another term for that is bare metal, but back long enough ago, this was just called computing, right? So in this case, you have your physical host, your server, the physical hardware layer at the bottom. You've installed whatever operating system you want on top of it. Then you've installed whatever binaries and libraries are necessary to run your application. And then you would have your application, one or more applications, installed directly onto this host machine. Now, what are some challenges with this setup? First of all, you can see that shared layer of binaries and libraries. It's shared across both of those applications. And so if your applications, for example, need different versions of the same dependency or have some dependencies that are somehow incompatible with each other, now we've got we've gotten ourselves into what is known as dependency hell. So we somehow need to either modify our application such that those dependencies are now compatible, or figure out a way to carve up the system such that we can have both versions of the libraries available, doing things like setting your path environment variables differently for the different processes, etc. And so that can be quite a challenge. You also, because of this dependency management challenge, you're more likely to have fewer applications on each host machine. And so it makes it harder and harder to achieve high utilization. So let's say application 1 takes 1 CPU core, application 2 also takes 1 CPU core, but we have this server-based system that has 64 cores. It can be very hard to sort of utilize that compute capacity effectively because of the challenges associated with managing dependencies for applications. You also now, if you are installing multiple applications onto the system, if you ever have an issue with one of those applications or do something that will mess up some underlying dependency, now you have this large blast radius, meaning changes or issues with one application can directly impact the performance of another application running on that same host machine. So it just makes it much more dangerous to modify things. Also, the startup and shutdown speed of a physical system is on the order of minutes. So to spin down that server and reboot it for some reason, that can take a number of minutes. And so it's just relatively slow if you want to try to achieve high uptime and eliminate downtime for your applications. In addition to that, creating new physical machines, sort of provisioning a new system, is very, very slow. So depending on my setup, if I have my own data center and I need to actually order the hardware and get it installed and hook up networking, that could be on the order of days or weeks. If I'm working with a co-location facility or a cloud provider that offers bare metal systems, that provisioning might be on the order of hours, but still quite slow relative to what we'll see as we evolve and sort of add in this concept of virtualization. And so that's bare metal. I think most people are familiar with working with bare metal, even if they don't realize it, because when you run things on your laptop or your desktop, you're installing them directly on the host. And so that is this concept of bare metal. However, that's not the only way to do things. And so these challenges really prompted engineers to come up with this concept of virtualization and adding virtual machines such that we can eliminate some of those challenges. And so in the case of a virtual machine, now this outer boundary is still the host, the physical system, the server. We've got our hardware. We may or may not have an operating system running on that hardware. I'll talk about that more in a second. But then we have what's known as a hypervisor. And so a hypervisor is some combination of software and hardware that allows us to carve up the physical resources. So think CPU cores, memory, access to storage or GPUs, other devices. It allows us to carve up that pool of resources into isolated, smaller pools that we can then install our systems onto. And so this hypervisor kind of gives us this virtual hardware layer upon which we can then install an operating system, install binaries and libraries, and install our applications. And so now, rather than having both applications on the single physical host, we now have application 1 and application 2, each with their own isolated virtual machine running on top of that hypervisor. And so there's two types of hypervisor. Type 1 means there's no underlying OS. These are running directly on the physical hardware. This is beneficial because you don't sacrifice any performance in that sort of OS to software virtualization layer. There's a small performance hit, but much less than if you have an operating system on the hardware and then a hypervisor on top of that. So things like AWS Nitro, so that's the hypervisor that Amazon Web Services is using to create virtual machines on their servers. VMware is a very popular virtualization company, and they have vSphere, which is a type 1 hypervisor. If you want to just create a virtual machine, let's say on your laptop, you're probably going to use a type 2 hypervisor. One such example is VirtualBox. So you can install this program VirtualBox, and then within that, you can create virtual machines for various operating systems, etc. And so how does this compare to those challenges that we saw with the bare metal systems? One, we've eliminated this dependency hell. So Now each virtual machine has an isolated set of dependencies, binaries, and libraries, such that our application can specify whatever dependencies it needs and not have to worry about the needs of other applications. Because of this, we're going to have better utilization, so we can carve up a big server CPU into many different smaller chunks, and each of those chunks can have its own virtual machine, and then we can install our applications accordingly. So this is what enables a cloud provider. You can go on and see, oh, I can choose between all these different machine types. They don't actually have all those different machine types installed in their data center. They have much larger machine types, and you're getting some sliver of that installed as a virtual machine. We've also reduced the blast radius significantly, such that now if something goes wrong with application 1 on virtual machine 1, that should be isolated from application 2 and virtual machine 2, and it should not cause any issues. And so because of that, we've increased the safety of making changes. We've also sped up the speed at which we can start and stop these things. So now it's still on the order of minutes probably, but faster than shutting down and starting a physical server. And then finally, one area where virtual machines have a big bonus over bare metal is that we can provision and decommission them much, much faster. And so we're all used to living in this cloud world where we can go onto our favorite cloud provider, click the button or issue a command, and have a new virtual server ready within minutes. Or if we're done with it, we can decommission it, and it can also be done, and we can stop paying for it within minutes as well. And so that's the second tier, or the second rung along this path of virtualization. The next one being containers. And so containers obviously are the focus of this course. They change things a bit further still. So now in this outer box, we've got our host, which could be a physical system. It also could be a virtual machine. So we can take either of those two concepts from before, and we can run containers within that context. You can see at the bottom, we've got either a virtual or physical hardware with an operating system. And then the key piece here that's kind of analogous to that hypervisor is the container runtime. So this is a piece of software that knows how to take a container image and run it within the host system. The key difference between virtual machines and containers is that virtual machines are running their own copy of the Linux kernel. And I'm talking only about Linux containers within this course. There are Windows containers, but that is a different topic for a different day. And so with Linux containers, they are actually they're sharing the kernel with the host operating system. Versus in a virtual machine, you have your own you have your own kernel, and you have a copy of your own operating system that's running. And so within a container, you're sharing that with the host. However, we're using certain features that I'll go into later of the Linux kernel to help provide isolation between the different container processes. And so you don't get quite the same level of isolation that you would with a virtual machine. You do get quite good isolation if you configure things properly. As we can see, now we have our two containers, both running on the same host. However, they are still isolated and have their own copies of binaries and libraries, even though they're sharing that underlying kernel. Now, there's a couple of different sort of types of software related to containers. The first category of which I'll call the desktop container platforms. So these are sort of container management systems. Things like Docker fall into this category, things like Podman. These are things that you would install on your development system to manage containers, manage container images, run containers, set up the necessary networking, etc. So these are kind of the holistic lifecycle systems. And then there's much more targeted or specific pieces of software called container runtimes, which include things like Containerd or Cryo. And these are very specifically designed to take a container image that adheres to the spec and run it with the necessary configuration options to provide that type of isolated environment that is shown in the image. Now, how does this compare to virtual machines and bare metal in terms of those challenges we saw before? Again, we don't have the issue of dependency conflicts because they each have their own underlying binaries and libraries. We've improved our utilization efficiency even further because we now, for each virtual machine, we had to have an entire copy of that operating system. So each of those virtual machine images is going to be on the order of gigabytes, whereas container images can be much, much smaller, because they're able to leverage that underlying OS. And so they're generally going to be on the order of megabytes. I have seen very large multi-gigabyte container images, but that's not ideal. But because of this, we're able to utilize the resources of the system much more effectively. Again, we have a small blast radius where we have some level of isolation, even if it's not quite as strong of an isolation as a virtual machine. We're able to start and stop containers even more quickly than virtual machines, so on the order of seconds. We're able to, in this case, starting and stopping a container is kind of equivalent to provisioning and decommissioning, so also on the order of seconds. We can bring up a new container from scratch and clear it out as well. And then the final sort of key piece, I think, with containers is that they're small and light enough that we now start to use them within our development environment. Sure, you could use something like VirtualBox. You could create a virtual machine that tries to replicate your production environment, but it's kind of slow and clunky, and not that many people do. Some people do, but many people don't. Containers are light enough that now more and more we'll start to actually run containers, and we're going to do this later in the course, run containers within our development environment such that we can have high confidence that our production environment is as similar as possible to that development environment. And that just decreases the likelihood that we're going to hit some small nuanced bug between the differences there. And so we're able to develop more efficiently using a technology like this. And so I pointed out here that this host can be a virtual or a physical machine. And so now we can get a little bit inception with it, where we have a host machine with virtual machines running on it and then containers running within those virtual machines. And so this is a very common configuration that you'll see most people who are working with containers in the cloud are going to have something like this, where you have multiple virtual machines, each running multiple containers. And so this is just combining all these concepts together. And the real challenge now becomes, how do I manage all of these containers across those virtual machine hosts? And that's where this concept of orchestrators comes in. And so things like Kubernetes, Nomad from HashiCorp, or Docker Swarm are these systems that are designed specifically to take containers and run and manage and schedule them across multiple nodes. And so in this case, the node is each of those virtual machines. And so when we get to the deployment section of this course, we'll talk a little bit more about this. But it's just important to know kind of the concepts of, hey, I'm starting with this bare metal server. My code has to run somewhere on some physical CPU. I'm carving it up into these smaller virtual machines that I'm able to manage a little bit more effectively. But then I also want to gain the benefits and the speed and the efficiency that a container provides. And so combining these different types of virtualization in this way that we see more and more companies using in this day and age. This chart just summarizes most of those challenges and trade-offs that I talked about before in terms of dependency management. Virtual machines and containers really shine. In terms of utilization, containers definitely win out just because it's much easier to get to pack applications more efficiently when running them in containers. From an isolation perspective, you can't get any more isolated than multiple physical hosts. If you're running application A on one server and application B on one other physical server, that's the strongest isolation you can get. Virtual machines still provide very strong isolation, and those hypervisors are these very optimized systems with a small attack surface area that have really been battle tested. And so I think isolation provided by virtual machines is almost as good as those from bare metal. Obviously, there could still be some unknown bug that causes a security issue there, but I think most people have quite high confidence in the isolation that hypervisors provides. And then containers, this is one area where they are less good than these other options, is they do provide some level of isolation. We'll talk about the ways in which they do that, but they don't give the same, they're not as strong. And if you make a configuration mistake, the level of isolation can be dropped significantly. So that's why I gave containers a yellow on isolation. Startup speed, containers win out. The ability to run containers within a development environment, because they're lightweight enough, means that we're much more likely to do so and therefore have stronger parity, or have our development environments and our production environments more similar to one another. This control row is one that I haven't talked about as much. This is just the fact that you can have full configuration control over the system in a bare metal context that you might not get in a virtual machine. So you only have control over the features or the specific configuration options that the hypervisor passes through or the container runtime passes through. And so maybe there's some specific type of GPU or hardware accelerator that is not yet supported by your particular container runtime or your hypervisor. In those cases, the bare metal system is going to win out, because if you need that specific hardware config, that might be the only way in which you can achieve it. And that leads into kind of this next row of performance. Obviously, a summary of red, yellow, green here can't fully capture the nuances. You don't take that much of a performance hit when you move to a virtual machine or container. However, I think one place that performance can win out on bare metal is because of that control. You're able to do things like, if you're running multiple servers, for example, ensure that they are directly next to each other on the same server rack, such that the networking latency is as small as possible, or ensuring that the storage devices that you're using are directly connected to that physical machine versus accessing them over the network. And so there is performance tuning that bare metal provides the opportunity to do. But overall, the performance is fairly comparable for most use cases across these different technologies. And then the final column there, just sort of how challenging it is to work with. And so if I'm buying and racking my own servers in a facility that's intensely difficult to do and manage, there are now providers that can give me access to bare metal systems and handle some of this operational overhead. But I think it's still more challenging than virtual machines, and more challenging still than containers, where I can spin something up and down very easily. And there's all of these services that have container runtimes such that as long as I provide a compatible container image, I'm able to run it within that system. And we'll see that optionality in a later portion of the course when we get into deploying our own containerized applications. And so now that we have a better understanding of the motivation and history of containers and virtualization technologies, I think it's useful to do a bit of a technology deep dive and start to understand the foundational Linux kernel features that software like Docker is using to make the magic of containers happen and provide those isolated environments that we described. Then towards the end of this section, we'll actually take a look at the Docker system architecture itself. There's 3 technologies that make up the core.
Okay, so break time, making a tea, and then I will be back. Okay, I had my break. Let's continue.
Of a container, and that is namespaces, control groups, and union file system. And there's three tech section containers happen and provide those isolated environments that we described. Then towards the end of this section, we'll actually take a look at the Docker system architecture itself. There's three tech.
Okay, I have to, excuse me, oof. So I have to take a note here. I have to take a moment to reflect again because I can feel that I'm losing interest, and partially it's because we just went through the history and motivation, right? And this evolution of virtualization with the bare machines, virtual machines, containers, virtual machines, containers plus orchestrators. And even though I just said previously that I'm gonna note everything down, I just watched them in one go, and then again I felt the disconnect happening. But you must understand that you don't actually have to really note everything just because you like. There should be critical thinking used here because the reason why is our use case for all of this is that because these are being used at the work, and so we have at least some understanding. I mean, this is, to really know deep down, it's a DevOps job. We don't know if we're gonna be a DevOps person ever. So I'm just trying to motivate you now that it's okay to watch and decide critically, okay, it's not really applicable for me, and I trust my judgment that it's not applicable, so I'm not gonna take time to actually really note it down because of time management or whatever. But yeah, I trust myself that I know that I can make a difference between what is important and what is not. And yeah, I don't know, because I see Linux building blocks. I have no. Okay, so this is important because I have very little thing I know about Linux, how it's working. So it would be nice. I mean, I think ideally you should note still everything because that's the point. That's the point. It's busy work. It's nothing but busy work.
Technologies that make up the core of a container, and that is namespaces, control groups, and union file systems. And now namespaces are a mechanism to environments that we described. Then towards the end of this section, we'll actually take a look at the Docker system architecture itself. There's three technologies that make up the core of a container, and that
These are free technologies. Free. There are free technologies that will make up the core of a container. Namespaces, control groups, and union file system. And we're gonna go through each of them in more detail. Namespaces. Oops, I didn't mean to do that.
That is namespaces, control groups, and union file systems. And now namespaces are a mechanism to wrap a global system resource such that from within that namespace, any processes running within the namespace, it appears as though they have their own isolated instance of that resource, and they cannot see things happening outside of their own instance. So for example, on the right here, we have a listing of the various types of namespaces. One very good example is the PID namespace, so the process ID namespace. Within a container, it is isolated with a PID namespace such that the process I'm running appears to be process ID number 1, even though there may be tons of other processes running on the host. From inside the container, we don't know anything about those host processes, and we essentially think that we are the only thing running in this system. Another good one to call out is the user namespace. So by using a user namespace, containers are able to map one user within the container to a different user on the host system. So we could be running as a root user with elevated privileges inside the container, but as long as that container is run within a user namespace that's configured correctly, that root user inside the container may actually map to a non-root user outside the container. And that's very important from a security perspective. In case there was an issue with one of our containers and an attacker was able to gain access to it and break out of that container, if we had properly set up user namespaces, then on the host, they would not have the same level of privileges that they had inside the container. C groups are a Linux kernel feature that allows
I didn't understand a single word from anyone.
you to organize.
I didn't understand a single word. Word. A namespace wraps up a global system resource in an abstraction that makes it appear to the processes within the namespace that they have their own isolated instance of the global resource. Changes to the global resource are visible to the other processes that are members of the namespace, but are invisible to the other processes. So there is a namespace called C group, which isolates the C group root directory. We have a network namespace, which has a flag, and it isolates the network. Okay, so it wraps a global system resource in an abstraction that makes it appear to the processes within the namespace that they have their own isolated instance of the global resource. Changes to the global resource are visible to the other processes that are members of the namespace, but are invisible to the other that are members of the namespace. Okay, so, and do we see the members here? Okay, we're gonna go more deep into that. Okay, fine. Anyway.
Namespaces are a mechanism to wrap a global system resource such that from within that namespace, any processes running within the namespace, it appears as though they have their own isolated instance of that resource, and they cannot see things happening outside of their own instance. So for example, on the right here, we have a listing of the various types of namespaces. One very good example is the PID namespace, so the process ID namespace. Within a container, it is isolated with a PID namespace such that the process I'm running appears to be process ID number 1, even though there may be tons of other processes running on the host. From inside the container, we don't know anything about those host processes, and we essentially think that we are the only thing running in this system. Another good one to call out is the user namespace. So by using a user namespace, containers are able to map one user within the container to a different user on the host system. So we could be running as a root user with elevated privileges inside the container, but as long as that container is run within a user namespace that's configured correctly, that root user inside the container may actually map to a non-root user outside the container. And that's very important from a security perspective. In case there was an issue with one of our containers and an attacker was able to gain access to it and break out of that container, if we had properly set up user namespaces, then on the host, they would not have the same level of privileges that they had inside the container. C groups are a Linux kernel feature that allow you to organize your processes into groups which you can then limit and monitor access to certain resources. And so on the bottom left, you can see within the file system under proc/c groups, we can see all the different C groups that are available. These correspond to different system resources, whether they're CPU, memory, storage devices, etc. And using C groups, we can specify a configuration for a particular process or group of processes on how they should be able to access those system resources. And so for example, on how a configuration for a particular process or group of processes on how they should be able to access those system resources. And so for example, we might have one application that is enabled to use up to 30% of the CPU cycles. We would use the CPU.shares C group. Maybe it can use up to 50 megabytes of memory. We would specify that with the memory.limit in bytes C group. And then we could also limit the amount of disk read that it has access to using the block IO throttle read bits per second device C group. Now, the reason that this is important is that it allows us to avoid what's called a noisy neighbor problem, where one application is very resource hungry and sort of starves the other applications of resources. By using C groups, we can isolate from a performance perspective each of our different processes and each of our different applications. Now, the third key underlying technology is what's called a union mount file system. A specific example of which that Docker uses is called overlay FS. It essentially allows you to take separate file systems and combine them into a unified view that you can then operate on. And so in the image, you can see we have a lower file system and an upper file system with various files.
I have to take a quick break because something is off around here. Just 1 second. Union Mountain File System overlays allows files and directories of separate file systems known as branches to be transparently overlaid, forming a single coherent file system. Contents of the directories which have the same path within the merged branches will be seen together in a single merged directory within the new virtual file system. How old is this video anyway? Not so old.
Files, we got file 1, 2a, and 4 in the lower layer. In the upper layer, we have a different file 2b, a new file 3, and then we've actually deleted file 4. When we combine these layers into the overlay, we end up with a combination of those two things, where the upper layer takes precedence over the lower, and so we have file 1, file 2b, and file 3. And so while namespaces and C groups are sort of what make containers possible, it's this concept of a union mount file system that makes containers practical. Because of this layered approach, we're able to share lower layers and cache those layers such that the amount of data that needs to be transferred and stored for container images is much, much smaller, because many images can share a common lower layer, and then only some subset of the upper layers can be modified, which enables us to move less data when we need to get a container image onto a system and allocate less space if we're running multiple copies of the same container. And so with those technologies, while you can interact with them directly, it's software like Docker that takes it and packages it into a really nice user experience. So rather than needing to know all the different commands to create control groups and move processes into them, or create namespaces and block off the different portions of our system in such a way, Docker has bundled that into an easy to use desktop application that we can install in our system and get all of that with a series of simple commands that we're going to learn throughout this course. And so this is a diagram of the Docker desktop application. There's a number of pieces here, so let's call them out in turn. On the left-hand side is the client application, and so this is the thing that we will be interacting with. There's a number of elements. There's the command line interface. So when I go to my command line and type docker run or docker pull, I'm interfacing with that Docker CLI. There's also a graphical user interface which gets installed. This is nice for browsing which images you might have on your system. You can do things like configure how much CPU and memory and disk space the Docker application has access to. So there's a number of nice user experience features that the GUI provides. There's also a credential helper. And so this is when we learn more about registries later on in the course. Essentially, a registry is a place where we can push images to and pull images from. And so in order to have a private registry, you need some way to log in. And so the Docker credential helper is a mechanism to help store the necessary credentials to do the authentication for that. And then finally, extensions are a relatively new feature of Docker that are third-party pieces of software that plug into the client and provide additional functionality in some way. And so that's the client application. When you install Docker Desktop on your system, it also creates a Linux virtual machine. So if I'm on macOS, there's no such thing as a macOS container. Instead, Docker uses a hypervisor, installs a Linux virtual machine, and then within that virtual machine, it sets up two things. It sets up the server host application. And so that's known as the Docker daemon or Docker D. That exposes an application programming interface, the Docker API. And so when I execute a command from the command line, let's say I do Docker run, that command gets passed to the Docker daemon, which is listening via that Docker API. And then it executes whatever the command that is specifying within that server host application. So let's say I did Docker run and then specified I wanted to run my container image 1. I might create, it would then go off and create that container 1A. Let's say I then issued that same command, Docker run with my container image number 1 again. I would get another container 1B. And so this Docker daemon is managing those container objects as well as things like networking and volumes all within this server host application. Finally, there's an optional Kubernetes cluster that gets configured and installed within that virtual machine. This can be a nice to have if you are developing for Kubernetes. You can leverage that cluster directly without having to install and configure a separate cluster. I mentioned for macOS, it's a Linux virtual machine. On Windows, there's actually two options. You can either configure it to use WSL, Windows System Subsystem for Linux, as the backend, or you can use Hyper-V as that virtualization layer to create a virtual machine. I think either of those are viable. When we go through the installation and setup in the next portion, we can talk through that in a little more detail. And then the final portion to call out on the right, I hinted at this, but a registry is just a place to store your container images and share those container images with your team or with the world or with wherever you're deploying your containers to. And so while it is not a part of Docker Desktop, it's useful to call out here because that Docker daemon, when it needs to get an image that it's not building locally, it's going to go off to some registry. Docker Hub is a great example of one such registry and pull that image into the host environment so that it can then run the container from it. There's also a little bit of confusion around Docker, Docker Desktop, and Docker Engine. I've highlighted a few of the subcomponents here that make up what's known as Docker Engine. And so that is the command line interface, so that Docker CLI, as well as the Docker daemon and the Docker API. Those make up what is known as Docker Engine, and that is the open source core of Docker. Because the Docker daemon only runs on Linux, you can only install Docker Engine on Linux. You don't get sort of this niceness of the Linux virtual machine and sort of the developer experience that the GUI provides. But if all you need to do is build, run, and interact with containers, then Docker Engine might be sufficient for your needs. In this course, though, because we're using Docker for development, and likely many of you are on Windows and Mac OS systems, we're going to install Docker Desktop so that we can leverage all of the developer experience niceness that Docker Desktop provides. At this point, I think we are ready to go ahead and install Docker on our systems and start using it.
My head hurts and yeah, I will eat, I think. Yeah, so I don't know if I should keep stream or what. I don't know. I have a decision fatigue. If I stop streaming, then it's very unlikely that I will return and continue. So I'm just gonna keep streaming, and at least also it will stop me from using my phone for stupid purposes. So break back, bring back. Oh my god, bring back the break.
One thing that
Ha! It was not muted the whole time, so that's amazing. Anyway, I was wondering why I feel like I want to have a coffee when I don't drink coffee, right? Because of this picture. Anyway, okay, so let's install the guy.
That is important to call out is that for personal use, Docker is completely free. You can use Docker Desktop without paying anything. However, if you're using it for commercial purposes and your team has either more than 250 employees or more than $10 million in annual revenue, it does require one of the paid tier subscriptions. So depending on how you're using it within your company, it may or may not be free. So that's just something to call out before we install it. But for personal and learning purposes, it is completely free. Now, to install it, we can just go to the Docker docs under docs.docker.com/getdocker. And so in preparation for this video, I actually uninstalled Docker. So I'm going to go ahead and pull open Chrome and go to that site. And so here I am at docs.docker.com/getdocker. It gives us options for Windows, Mac, and Linux. So choose whichever operating system you're on, and then it will have some additional system requirements and information that you're going to need. I'll just click Docker Desktop for Mac with Intel, and it'll start downloading. It is quite a large file, so we'll see. Hopefully my home internet is fast enough. Down below, it has information about system requirements for depending on the type of system that you're running. So you just want to go through and read these. The installation process is pretty much just like any other desktop application. Here it's downloading that .dmg file. I'll then open it, drag it into my applications folder. On Windows, similarly, a pretty straightforward installation process. The one thing to call out is the two different options for the backend. So I described in the architecture diagram how you have your client running directly on your system, but then you're going to have this virtualized environment where the Docker daemon is running. And so this is choosing whether you want that Docker daemon to be running within WSL or using Hyper-V as the backend system. If you are on Windows, I would probably just go with this WSL backend, as that's kind of the default option here. So it looks like my installation file has finished. I'll drag it into applications.
Okay, so the performance of the laptop is completely shambles. But we are installing Docker. So we are 2 hours, almost 2 hours into the stream, and we are installing Docker.
It expands from the 600 megabyte download into a 2 gigabyte install. And now I should be able to just go to my applications and click on Docker. It's verifying. It asks whether I want to trust it or not. I click open. And so now here is that graphical user interface. One thing that I will call out is you may want to go under settings and then resources. And here you can specify how many of your system resources that Docker as a whole should have access to. So here it's defaulted to 4 CPUs, 10 gigs of memory. I'm going to give it access to a little more memory. The defaults are likely fine for just getting started, but if you find yourself running up against resource constraints, modifying these resource configurations can be very helpful in alleviating those constraints. In order to have those changes take effect, you have to click apply and restart. And so I'll do that now. Now, at this point, we can...
So what I'm going to do, I'm going to start using my headphones because I cannot have even the brain power for this to even think about when I should mute myself or when I shouldn't. It's crazy. So let me just do that while Docker is still installing. So
can run Docker commands. And installing that application gave us both the CLI as well as the Docker daemon. And so
I'm impressed. It's not even bad. There's no actual any noise. I just plugged it in directly to the M audio speaker.
let's run our first container. One fun example that we can use is the whale-say container. And so I can do it here. It's defaulted to 4 CPUs.
But see, we have here the prime example of our time management problem, because we knew that we're gonna have to install it, and but I just wanted to run away. Like I was like, no, I have to eat right now. Whereas if I just start the installation, I would be having the break now to eat. Would have made so much sense. I even forget English, guys. It's crazy.
Use 10 gigs of memory. I'm going to give it access to a little more memory. The defaults are likely fine for just getting started, but if you find yourself running up against resource constraints, modifying these resource configurations can be very helpful in alleviating those constraints. In order to have those changes take effect, you have to click apply and restart. And so I'll do that now. Now, at this point, we can run Docker commands, and installing that application gave us both the CLI as well as the Docker daemon. And so let's run our first container. One fun example that we can use is the whale-say container. And so I can do Docker run Docker/whale-say, and then the command is going to be cow-say, and I'll just say, hey team. And so if I run that, it's going to go off and find that public whale-say image, download it from Docker Hub, so we can see it downloading now. And each of those lines corresponds to one of the layers in that overlay file system. And so it's downloading each of those images onto the host system such that we can then run a container from that image. And we see it took the phrase that I put in here and gave us this nice ASCII art output with that phrase built in. And so with that, we have pulled an image from Docker Hub, run a container from it, and provided a custom command. So that's kind of the most basic thing that we can do with a Docker image. And so that's a fun example, but let's do something a little more useful. Let's say we needed a copy of Postgres 15.1 running for our application. We can just issue a Docker run command, and then I'm doing two options here. One, I'm setting the Postgres password environment variable. That's just something that's needed. The container won't start if you don't set a password. And then I'm also publishing port 5432. And so because these Docker containers are running on an isolated network, the only way that I'm going to be able to connect to it from my host is to publish that port. And so that publish command is saying take port 5432 on my local host, my system, and connect that to port 5432 inside the container. I'm then specifying the Postgres image and specifically version 15.1 running on the Alpine operating system. Again, it didn't have that image locally, so it's going to pull that from Docker Hub. Once it finishes pulling, it then starts up the image, and now we have the database system running inside that container, ready to accept connections. Just to show that it is actually running and accepting connections, we can open up pgadmin. And we can see I've added this Docker database, and it was able to successfully connect to it. And we can, for example, run a query. I could do select star from information schema dot tables and run that. And we get all the tables from that information schema within the database running inside the container. Hopefully this gets you excited about the possibilities of what running inside of these isolated container environments can provide in terms of your development lifecycle. Now that we've run a couple of simple containers on our system, I want to...
So, installation finished. We are happy, but we do have to restart. So, day one will continue. I mean, yeah, if we would stream now in a virtual machine or whatever, then if we wouldn't be affected. But no, if we would install all of this now in a virtual machine. But whatever. So I guess part 2 in a moment.